Okay, so now we're moving on to a new topic, multiple regression. So the learning objective for this chapter is to understand statistical models for multiple continuous variables. So we have just dealt with simple linear regression where we have one x variable and one dependent variable y. So now we are going to extend all those ideas to handle more than one independent variable. So we could simply write our equation in a way similar to the simple linear equation where we add in extra x's. So we can write this as y equals b0 times 1 plus b1 times x1 plus b2 times x2 up to bp minus 1 times xp minus 1. So this would be with p minus 1 x variables. And again, it's plus epsilon, our random error. So this is written slightly differently. Rather than using capital A for the intercept, we're now using B0 as the intercept. And we're multiplying B0 by 1 so that we understand that we can see it as all of these coefficients multiplied by something. So B1 to BP minus 1 are the slopes. So previously we just had one slope B. So B1 is the equivalent of B. So why would we want to write it this way? Well, one of the reasons for writing it this way is that if we use matrix and vector notation, then we can write this in a very simple way. So for those of you who don't know matrix and vector notation, you can just ignore this section. But a matrix generally means a table of numbers. So X here is an n by p matrix, meaning we have n rows corresponding to our n data points and p columns corresponding to the p elements we're multiplying b by. So remember, we've got a column of ones corresponding to the multiplying of b0. Then we've got the column of x1 values, the column of x2 values, up to the column of xp minus 1 values. And a vector is just a simple case of a matrix that only has one dimension. So it's basically a column of numbers. So y is an n by 1 vector. So it has n values, y1 to yn, which correspond to our n data values. And e is the vector of error. So that's all the little epsilons put together in a vector. So again, we have n values for e, which correspond to the n rows of our vector of errors. And then lastly, b is again a vector. B is our p by 1 vector. Remember, we have p coefficients, b0 up to bp minus 1. So we can write this whole thing as just being y equals xb plus e. So I'm not going to go into the details of how we multiply matrices and vectors together, but we can just think of this as a very simple representation. Now, why is this so helpful? It's not just because we can write it simply, but it turns out we can also write the estimates for B in a very nice and simple way. So let's have a look. So it turns out that we can write the estimates for B. So that's little b again, but this time remember this is a vector. We've got p estimates in our column vector little b. So this can be written in matrix notation as x transpose x inverse x transpose y. So what's x transpose? So we transpose a matrix means we swap rows and columns. So x transpose x means we swap the rows and column of x, multiply it by x. Inverse basically means the inverse of a matrix is the matrix when we multiply by that original thing, we get what we call the identity matrix, which is ones down the diagonal and zeros everywhere else. So in matrix and vector notation, we can write B. So we don't need to necessarily understand what x transpose x inverse x transpose y all means. The key point is that you can see it depends only on x and y in a particular way. And if we think about the fitted values of y, that's x times little b, where we're using the estimates for b. So that can be written as H times Y, where H is this projection matrix X, and then X transpose X inverse, and then X transpose. So this is a particularly interesting matrix which tells us how to get from our observed Y's onto our fitted Y's. So this is what we call a projection matrix, or it's sometimes called a hat matrix. So that takes us from our n-dimensional space, because we have n data points, onto a p-dimensional space, because remember we only have p coefficients of x. So we're trying to find the closest fit to y in terms of the squared errors, where n is the sample size and p is the number of parameters in the model. So the simplest case, the null model, is just where y fitted is the mean of y's. That has a hat matrix that just projects y onto the mean of y. The simple linear model, which we just dealt with, has p equals 2. That's projecting y onto a two-dimensional space. So that's the plane that goes through the mean of y and through x. So that has equation a plus bx, remember. So conceptually, if we were in the classroom, I would use the video projector to try and explain what the idea here is. So if I put a 3D object up between the projector and the screen. So for example, if you put your hand up between the projector and a screen, you get a 2D shadow, a 2D projection on the screen of that 3D object. So what we're trying to do is to get a 2D projection that retains most of the useful information. So if you hold up your hand where all your fingers can be seen clearly, this contains clearly most of the information about what the shape of your hand is. If you turn your hand through 90 degrees so that the fingers are all perpendicular to the projector, then clearly you can no longer see the fingers. You would be missing all the key information about what a hand looks like. So this is a projection from 3D onto 2D. So that would be like having a data set of 3 data points and we fit a regression line with just one x variable. So we can show using calculus that this is the optimum solution under quite general conditions. We don't actually need to know this formula, but it turns out to be very helpful if we need to write it down. So we're going to assume that all these calculations will be done using either a spreadsheet like Excel or a statistical package. So what about the error variance, S squared? So if you remember in the previous case, we had the sum of the squared residuals divided by n minus 1. So the difference here now is that we're dividing by n minus p because we need p data points in order to fit the line exactly. So until we have at least p data points, we have no information about S squared because it will be a perfect fit through anywhere up to p points. So we end up with n minus p, in effect, data points left over that help us to estimate the error variance. And then similarly, for when we want to test the slope with respect to, say, xi, which would mean testing bi is equal to 0, or finding a confidence interval for bi, the idea is very similar to simple linear regression, where the 95% confidence interval for capital BI is just little bi plus or minus the t cutoff value times the standard error of bi. And similarly, we will reject bi at 5% if bi is outside that interval. So what is the standard error of bi? Well, it turns out we can write this in a very simple form. It's just the ith element of x transpose x inverse, taking the square root, and then we multiply this by s. So again, the standard error of any of these coefficients is proportional to s, but the proportionality constant depends on this x transpose x inverse matrix. We take the square root of that element of the ith element. That means the diagonal element. So again, we're going to use a computer to calculate both the t-statistic and the standard error of bi. We don't need to do this ourselves. but essentially we're using the same conceptual framework as with simple linear regression. So we're going to start by looking at a nice simple example. This is an example about predicting the auction price of grandfather clocks given the age and the numbers of bidders. So I need to explain a little bit before we look at the data set and the results. So what is a grandfather clock and what do I mean by the auction price? Well, the auction price, I'm sure you've all at least looked at eBay if you haven't bought things on eBay. So eBay is a way of finding an auction price for buying and selling goods. But the type of auction we're talking about here is a more traditional auction where everybody sits around in a room and somebody at the front gives everybody a chance to bid, and the person who bids the highest gets to buy the item. So eBay is a little bit more sophisticated. I don't want to go into all the details of it. So eBay actually is a very clever way to sell things, but a traditional auction, clearly you would expect that the more valuable the item, the higher the price, and also the more people who bid, the higher the price. Now, this is a little bit of a cheat, one could argue, because you won't know the number of bidders in advance only once you turn up at the auction. So one could argue whether this is truly something that's useful in a prediction model, but this is just a nice simple example. So what exactly is a grandfather clock? So a grandfather clock, we need to understand a little bit about history of clocks. So until the end of the 19th century, clocks were not very accurate. So a grandfather clock is essentially a clock based on a pendulum. So I'm sure you all remember from your high school physics that the time period for a pendulum depends on the length of that pendulum. So if the length of the pendulum stays constant, then actually the clock should work quite well. We should be able to find a mechanism to calculate time by looking at the swing time of a pendulum. So what's the problem? Well, pendulum clocks were originally made often of metal. Now, what do we know about metal? We know about metal is that when the temperature changes, then the length of a metal pendulum will change. As it gets warmer, the metal expands and the pendulum gets longer. So the problem was then that as the temperature changed, the time period of the pendulum changed, and so the accuracy of the clock would change. So what was the key advance? So the key advance in the end of the 19th century is that somebody realized that different types of metal have different coefficients of expansion. So by constructing a rather more sophisticated pendulum, you could balance out the different expansion rates of different types of metal in order to end up with a pendulum which had very close to a constant length. So that meant these clocks were much more accurate than previous clocks. They were able to keep a very constant length and hence a very constant period, and hence remain very accurate. But these pendulums were relatively large and they were relatively expensive. So what happened was that middle to upper middle class or wealthy families would have one of these clocks in their house. They perhaps could only afford one of these clocks, and it would be put in a very nice wooden case because it was something very valuable which people thought would remain valuable for a long period of time. So these grandfather clocks have remained value, even though these days any digital watch is far more accurate than the grandfather clock. These have retained value as a piece of furniture with a very nice mechanism inside and a very nice wooden case. So obviously you would expect the older the clock that they might be more valuable, and as I said, if the number of bidders is greater, we would expect them to be the price to go up. So let's have a look at the output we get from a statistical package for a data set like this. So on the left-hand side, we have the plot. This is showing us the actual prices, the y-axis, and the predicted prices are the x-axis. So this is the combination of age and bidders. This is our best prediction. And you can see the predictions look quite good. The R-squared value is nearly 90%. So nearly 9/10 of the variability around the average price disappears if you look at the variability around the fitted line. So that's quite impressive. So let's have a look on the right-hand side, the statistical analysis. So this shows us that the coefficient of age, this is age in years, is about 12.7. The standard error for that is about 0.9, so the T ratio is about 14. And for bidders, the coefficient is 85.8 with a standard error of 8.7, so the T ratio is nearly 10. So you may remember that T ratios bigger than about 2 will usually be significant. So this is very strongly significant as assessed by the observed significance level. So there's essentially no argument that there is a linear component with age and a linear component with bidders, and that overall we end up with a model which works quite well. Okay, so let's have a look at a more challenging example. That example, as I said, both of our variables were statistically significant, and there was nothing too obviously wrong with it. So let's look at a more tricky one. So this example is looking at oxygen update for runners. Oxygen uptake for runners. So why do we want to know the oxygen uptake for runners? So in fact, I was involved with a study that looked at something like this in the past. So imagine that we want to look at the fitness of young people in Hong Kong. And in the ideal world, we'd bring each of these young people into a laboratory and we would check how much oxygen they are taking in their breathing as they run at different rates, so we can understand how fit they are. Now, unfortunately, that's very expensive. So how do we handle this? How do we handle dealing with a bigger group of people? Well, we do a small study like the one we're looking at here inside a laboratory, but we have to do it in such a way that we can also do it safely. We can extend this by doing something safely in schools. So first of all, you have to be careful because you don't want these children to do something which could be hazardous to their health. You don't want any of them to have a heart attack because they've overexerted themselves. So you need to find some way of looking at fitness that doesn't require people to run too fast. Okay, so we need to think something about that. Secondly, we can't afford to put oxygen masks on everybody and assess their oxygen uptake. So what we really want to do is to have something that takes into account how they run. So we do something that's called a shuttle run. So this is something that's feasible in almost any school. So in Hong Kong, most schools don't have a proper running track, but they all have a playground. So what we can do is ask young people to run back and forth across the playground, and we can suggest that they choose their own speed for running back and forth, and we ask them to run a certain number of times back and forth across the playground, and we look at several different things in order to understand their fitness. So obviously we want to look at their pulse rate. So that would be what would be the dependent variable in that situation, and we want to look at how their pulse rate depends on their fitness and on their run time, right? So obviously the faster you run, the higher your pulse rate. So that's why we want to understand how the oxygen uptake depends on people's run time and on their pulse rate. But in this particular study, we actually have 3 different pulse rates. We have resting pulse rate, running pulse rate, and maximum pulse rate. So what do these 3 things mean? So the resting pulse rate is what was your pulse rate before you start the exercise. In other words, when you're at rest, does your heart beat fast or slow to start with? The running pulse rate means at the end of your run, what was your pulse rate at that moment? But you'll see we also have here the maximum pulse rate. So you might say, surely the maximum pulse rate will be at the end of the run. But actually that's not necessarily the case. Sometimes the pulse rate continues to go up even after you stop running. So what we're trying to do here is to understand how the oxygen uptake depends on your run time. Obviously, we'd expect that shorter run times will mean you need more oxygen. We want to know how it depends on the resting pulse rate, the running pulse rate, the maximum pulse rate. And in this particular study, we also wanted to see what was the effect of age and weight. So, you see we've got this plot here. This says R squared is about 82%. So this isn't a great model, but we're explaining quite a lot of the variability. And on the right-hand side, we have the statistical test for each of these covariates, each of these variables. So we can see that for age, the result is significant at about 1.6%. Weight does not appear to be significant. Runtime is very strongly significant. Resting pulse is nowhere close to significant, 65%. Running pulse is significant at about 1.8%. And maximum pulse again doesn't appear to be significant at about 37%. So this leads to an obvious question. How do we select the optimal set of independent variables in our regression model? So we need to think very carefully, because including variables in a model, we may include them for 2 different reasons. First of all, because they're theoretically important or they're statistical controls. In other words, we want to remove the effect. So age and weight, for example, we may want to remove the effect of age and weight so we can understand how runtime and the pulse rate affect the oxygen uptake after removing age and weight effects. And then the second reason that we would include variables in a model is because they're statistically important. In other words, when we test capital B as 0, we have rejected that hypothesis. So theoretically important variables that we need to statistically control for are called confounders. So if you go back and look at the earlier chapter, there is some discussion of confounders. In this case, we will include the variables even if they're not statistically significant. So in an ideal world, we could randomize that experiment and remove the problem of confounders, but this is often not possible unless we have a designed experiment. So we often have observational data, so we can't control people's height and weight directly. So that's why that would normally be a confounder. So let's start with a very broad question first, which is, how do we test our complete model? So rather than looking at each of the individual variables, what if we want to test, first of all, is our model as a whole useful? Right, so if you go back and look at the previous slide, you will see underneath the graph it says p less than 0.0001. So that actually is the significance level for the overall model with all our variables put in together. Now, from looking at the right-hand side, you might well say, well, maybe we don't need all those variables, but at least do they collectively have a value? Okay, and this says the answer is probably yes, but how do we get that result? So we're going to introduce a new concept. This concept is called analysis of variance. The idea behind analysis of variance is to try to partition the variability into different parts with different explanations that add up to the total variability that is related to the total variance. So this variability we're going to measure in terms of the sum of the squared deviations. So SS is just the abbreviation for sum of squares, which means the sum of squared deviations. So we're going to try and partition, which means split up this variability into different components. So we start out with the total variability. This is just the variance for y times n minus 1. So that's just the sum of the squared deviations of the y's from the average value. So this is the variability we're starting out with. What we hope is that we can explain much of this variability by fitting our model. So after we've fitted the complete model, we end up with a little bit left over. That's what we call the residual. So the residual sum of squares is just the sum of squared deviations of the y's from our fitted y's. So that's just the sum of our squared residuals, the same as in our simple linear regression model. So this is just n minus p times s squared. So the difference, meaning the part we did manage to explain by our model, the model sum of squares, is just the difference between these two things. So it's the variability, the sum of squares about the average value minus the sum of squared deviations from the fitted values. So that's how much the model worked with. So for each of these sum of squares, we also have the degrees of freedom, which is the dimension that this part attracts to. So that the degrees of freedom for the total sum of squares is just n minus 1 because we have n data points, but we've subtracted off the average value. So we in effect have n minus 1 degrees of freedom. For the simple linear model, the model degrees of freedom was 1, and the residual degrees of freedom was the difference, which was n minus 2. So in general, with a multiple regression model, the model degrees of freedom is p minus 1. That's our number of independent variables. And the residual degrees of freedom is the difference, meaning n minus p. So in our table, we're going to create an intermediate stage, which is the mean square. So the mean square is just the sum of squares for each of these components divided by the degrees of freedom. So the model mean square is just the model sum of squares divided by the model degrees of freedom. The residual mean square is the residual sum of squares divided by the residual degrees of freedom, which is just s squared. So if the null hypothesis is true, remember the null hypothesis true would mean that the model doesn't help at all, meaning the model sum of squares should also just be random variation. So that the model mean square and the residual mean square should both be estimates of the same variance. So the ratio of these two should be around 1. However, if the null hypothesis is false, we would expect that ratio to be large. So our test statistic is the ratio, it's the model mean square divided by the residual mean square. We call this the F statistic, with model degrees of freedom for the numerator and residual degrees of freedom for the denominator. And we will reject the null hypothesis that the model is of no use if f is large enough. And we can easily look up the f distribution. So an f statistic is something like the ratio of two chi-squared variables. So the null hypothesis would be that all the bi's are equal to 0. Now you might say, if I go back to the simple linear model, what's the difference between this F statistic and the T statistic we used before? Well, actually, it turns out if we square the T statistic in simple linear regression, we get the F statistic. So for a two-tailed t-test, the F statistic gives us exactly the same p-value, exactly the same observed significance level, regardless of whether we use the F test or the two-tailed t-test. So what about the multiple regression model? Well, this is what we call the Omnibus Test. It's the test that combines all the individual t-tests in one overall test. Clearly, if we can't reject the Omnibus Test, there's no point in looking for a best model, because it means even if we look at all the variables together, we don't have a better fit than just using the mean value for y. Now you might say, can't we then also divide up the model sum of squares amongst the variables? Unfortunately, that doesn't always work unless the x's are all uncorrelated. So if we had designed this experiment to have the x's all uncorrelated, then it turns out we can divide up the model sum of squares into the sum of squares for each variable. Otherwise, the sum of squares we get for each variable depends on the order we added in, because it's saying how much does that x explain given the other x's which we've already added into our model. So we can also expand the idea of r squared to what we often call capital R squared to distinguish it's the proportion of variation explained by our set of variables. So if we go back to the analysis of variance table, r squared is just a model sum of squares divided by the total sum of squares. So obviously, if we have a good model, we would expect r squared to be large, hopefully close to 1, because that would mean nearly all of the total sum of squares is explained in the model sum of squares. So on first glance, it looks like choosing models is very simple. Why can't we just choose the model that has the largest value of r squared? But unfortunately, it turns out that this has a serious flaw, because each time you add a new variable, r squared will increase, even if that new variable is unrelated to y. So that means r squared is only useful in comparing models which have the same number of variables. If we want to compare models with different numbers of variables, we need to use something else. We need to use what's called adjusted r squared. So we can look at r squared and adjusted r squared using these formulas below. So r squared, remember, then is just 1 minus the residual sum of squares over the total sum of squares. That's the same thing as model sum of squares over total sum of squares, because the model sum of squares is just the total sum of squares minus the residual. So we can look at that as 1 minus the residual sum of squares over n minus 1 divided by the total sum of squares over n minus 1. You might say, why have I added in n minus 1 twice? It's to show you that this is a bit problematic, because when we looked at the mean square, we said that the total sum of squares, yes, we should divide by n minus 1, but the residual sum of squares should be divided by n minus p. In other words, there is a bias in r squared towards more complicated models. So the adjusted r squared is just 1 minus the residual sum of squares over n minus p over the total sum of squares over n minus 1, which is just 1 minus s squared over s0 squared, where s0 squared is just the variance of y. Right, so this is in a way to adjust for some of the bias in r squared towards models with more variables, because you can see here that maximizing adjusted r squared is equivalent to minimizing s squared, right? So these two things are equivalent because s0 squared is fixed within our set of models, because that's just the variance of y. So what we're looking for is a model which has small s squared. So in fact, if p is small compared to n, then the adjusted r squared will be close to r squared, because n minus p over n minus 1 will be close to 1. So in fact, if the number of parameters is small compared to the sample size, there isn't going to be too much difference. But if we come back and look at our example just before, so this is our example from the auction example first. If we looked at the auction example, this shows us the analysis of variance table, and it tells us the f-test. So this says the total sum of squares is 4791194. The error sum of squares is 514034. So the difference between those two gives us the model sum of squares. The model clearly has 2 degrees of freedom because we have 2 covariates, which were age and number of bidders. there were 32 data points in this data set. So n minus 1 is 31. 31 minus 2 is 29. So you can see how we get the degrees of freedom. If we divide the sum of squares by the degrees of freedom, we get the mean square for our model is 2138580. The mean square for the error is 17725. So the ratio of those two is 120. So f values bigger than about 2 will often be significant if n is reasonably large. So this is an enormous value for f, and it's highly significant. And if we look above, you'll see in this particular case, the R-squared value is 89.3% roughly, and the adjusted R-squared is 88.5%. So it doesn't make too much difference. The root mean square error. What's the root mean square error? That just means S. So JMP doesn't give S squared, it gives S. So this says S is about 133. And it's also telling us the mean response and the sample size. So that one wasn't really very interesting because that one we said it was obvious we need both the variables. So overall we have something strongly significant, and individually each of the variables were useful given that the other variable was already in there. So how do we select a model? So I'm old enough to still remember when computers were very slow. I'm even old enough to remember that we didn't generally have our own personal computers. We had to use a shared computer, and the way that we input our request for that computer to do some calculations was using punched cards. And in those days, you would submit your task for the computer to do in the morning, and you would come back in the evening at the end of the day, and if you were lucky, you had your results back. You would then perhaps need to make a correction or a change some of your punch cards, resubmit the task, and hopefully by the next morning you would again get an answer back. In other words, you only got 2 sets of answers per day. So it was a very different culture from today when we essentially expect to get instant results in our calculations. So in these days, when it took a long time to get answers back from the computer, the idea was not to try and give the computer one task to do, but a whole sequence of tasks to do. Hopefully you would then get a whole sequence of answers coming back twice a day. So the idea originally for fitting linear regression models, multiple regression, was to do something called stepwise regression. So the original idea was you start out with your null model, and then you look at all your possible x variables, and you say which one seems to be most useful. So most useful would mean which one has the biggest t statistic, and the one that had the biggest t statistic, you would add that variable into the model. And then you would say, okay, having added that variable into model, now let's look at all the other variables and to see which one has the highest t statistic when you add that to the one you've already added. So you keep on adding variables until there were no variables left that still have a significant test result. So this was called forwards stepwise regression. Now the problem was that this process has 2 flaws. First of all, it tends to yield models that have too many variables, that are too large, because we're doing many tests and we're choosing the one that is most significant from a range of tests. So that means that the true significance level of the model was actually much higher than claimed based on the significance of each test. So the risk of falsely rejecting the null became much higher than claimed. So that was the primary problem. But there was a secondary problem, which we might miss some good models, because if you have a variable that's only good if it's included together with another variable, maybe it never gets added. So if x1 and x2 together are very useful, but x1 and x2 individually are not very useful, then you would never include them into your model. So then people realize, okay, there's an alternative. Why don't we include all the variables to start with, check that that model is significant using the analysis of variance F test we just introduced, and then we drop variables out one at a time until all the variables in our model are significant. So this is again checking, is each variable significant given or conditional on all the other variables already being in the model. So this is called backward stepwise regression. Unfortunately, this model also has those same two problems. And it turns out we may have an additional problem that we call collinearity. So what's collinearity? Okay, so what is collinearity? So collinearity literally means in a line. It means that different sets of independent variables provide almost the same information. So this is quite common if we have a large number of variables, again, particularly with observational data. So with an experiment, we would usually choose the x values to ensure that they're not correlated, and we'll come back to this point when we consider experimental designs. But if we have observational data, it's quite possible that with a large number of variables, at least one of the independent variables can be predicted well from the others. So this is the problem of collinearity. So what happens with collinearity? Let me just go back to Zoom again. So collinearity is a problem in two senses. First of all, it may be hard to estimate the coefficients accurately. And secondly, it may make it a little bit hard to decide which variables to include into our model. Now, the first part of this you may find very strange. How can it be hard to estimate the coefficients accurately? Well, it turns out that this is really a problem with numerical analysis. That if your variables are correlated, it may be actually a computational problem. And in fact, this turned out to be a serious problem with certain naive statistical packages. So people who wrote their own statistical packages, who didn't know much about numerical analysis, sometimes had problems with this. So the most famous example of this was the early versions of Excel. So when Microsoft first started selling Excel with some statistical calculations in it, it was discovered that the statistical calculations were sometimes wrong, meaning that the numerical errors were so large that you were actually getting the wrong answers when you applied it to a data set, and it didn't warn you that the accuracy was a problem. So we're actually going to look at a particular famous data set which has been used in the past to illustrate the accuracy of estimation problems. And it also turns out to be an interesting example to look at the second part, which is deciding which variables we should be including in our model. So this famous data set has 6 independent variables, x1 up to x6. So let's have a look at this data set. So let's first of all look at each of the x's individually. So in the past, some people, in fact not just even in the past, some people think that if I have many x's and I'm trying to decide which ones to put into my model, what I should do is first of all look at each of the x's to decide which ones to put in together. And this turns out to be a very bad idea. So this data set also illustrates that point very well. So this is showing our first 3 x's. So don't pay too much attention to the numbers underneath. But if you look at them, you can see the first 2 x's, so x1 and x2, both look like they're quite good predictors of y. And you'll see the R-squared values are about 94% and about 96%. So both x1 and x2 look to be very good predictors of y. And they're both very strongly significant if we do a statistical test. If we look at x3, you can see this is not very good. The R squared is only 25%, and the significance level is only just significant at 5%. So all of these x's do show, however, an increasing trend, meaning as x1, x2, and x3 increase, then y increases, right? So we've got two good predictors, one not very good predictor. So a lot of people would say, okay, that means we need to include x1 and x2, but we probably don't need to include x3. So let's have a look at the next three x's. So now if we look at the next three, you can see that x5 and x6, the two on the right, both again look very good. x5 explains about 92%, x6 explains about 94%, and again x4 doesn't really look very good. It only has an R squared of about 20%, and it's not even significant at 5%. The observed significance level is about 7%. Right, so this naive approach, which I still find many people take, would be to say, well, we need x1, 2, 5, and 6 in our model. Doesn't look like we need 3 and 4. But I want you to remember that all of these variables had a positive coefficient. Okay, so particularly 1, 2, 5, and 6, but also 3 and 4 had positive coefficients, even though x3 was only just significant at 5% and x4 was only significant at 7.5%. Okay, so let's now look and see what happens if we put all the x's in together. So the good news, first of all, the R squared goes up to over 99%. So of course this is a much more complicated model, but you can see even the adjusted R squared is over 99%. So this is clearly a much better prediction model than the individual x's. So that's the good news. But now have a look at the parameter estimates and the t-tests. So first of all, you will see that x1 and x6 both have positive coefficients still, but x2, 3, 4, and 5 all have negative coefficients when we fit the model together. Okay, so let's have a look at the t-statistic. It says x1 not significant at all. What? x1 looked really good, right? x2 not significant at all. x3, which wasn't very useful, is now strongly significant, 0.25%. x4, which looked to be the least useful, is now the most useful, significance level of 0.09%. x5, which again looked pretty good, not significant. x6, so the only one of our four that we thought was good to start, of our six that we thought was very good, was x6, still in there at 0.3%. So we can see that 1, 2, and 5 don't appear to be useful when we put them together with x6, whereas x3 and x4, which weren't very useful, have now become useful. So if we look at the three which are strongly significant, you'll see that 3 and 4 are both negative, while x6 is positive. So how can this happen? How can we go from a situation where things which were strongly significant change sign and other things turn out not to be useful? So let's look at something very different. We're going to look at a scatter plot for the x's. So we're not going to include y for the moment. This is just about the relationship between the x's. So if you look at the scatter plot, it becomes very clear what is going on. x1 and x2, very highly correlated. x1 and x5, very highly correlated. x1 and x6, very highly correlated. x2 and x5, highly correlated. x2 and x6, highly correlated. x5 and x6, highly correlated. So the four variables that we thought were very useful to start with are all on a pairwise basis highly correlated. So 1, 2, 5, and 6. So that means that a lot of the information which each of them appears to be giving us in predicting y is common information. It's shared information. And if we go back and look at the model we fit just here, this implies that x6 is the best source of the information that x1, x2, x5, and x6 share. And that once we have x6, that it doesn't look like we need at least all of 1, 2, and 5. Now we have to be a little bit careful here because maybe we still need one more of 1, 2, and 5. This is just saying we don't need all 4 of 1, 2, and 5. So what about 3 and 4? So remember 3 and 4, if you look at it here, you can see that x3 and x4 are essentially uncorrelated with all the other variables. In other words, x3 and x4 include information that is separate from the information that is shared between x1, x2, x5, and x6. So what does that tell us? So that means that 1, 2, 5, and 6 strongly positive correlated is collinearity. They have a lot of common information. Now, I didn't tell you what these variables were. In fact, it turns out this is econometric data, and that x6 is the year. So in fact, this is data on how the US economy changed after the Second World War. So generally what was happening was everything was improving in the years after the Second World War. All that economic energy which had been put into the war effort, into building airplanes and ships and weapons and munitions, was converted into constructive energy. And so generally the economy was growing. So what we're saying is that once we know the year, that 1, 2, and 5 actually don't have anything particularly useful to tell us after we've taken into account the year. So the year is the most important of those 4. But it turns out that x3 and x4 have additional information which is separate to the year. They're telling us something else about the economy in terms of how well things are going. So that's just a little bit of warning about, yes, we should not assume that we can just look at the variables individually and know whether in combination they will be useful, at least if it's possible that our x's are correlated. So as I said before, if we were able to design an experiment, we could design the experiment to have the x's uncorrelated, so this problem wouldn't occur, and we could look at the x's without having to worry about the correlation between them. So we'll come back to experimental design later on. So having looked at forward stepwise and backward stepwise, one other possibility is to do what we call mixed stepwise, which means we, after each step, we try both adding and deleting variables. Right? So we do whichever one increases the significance the most. As I said, stepwise models were originally popular because the computer power available was limited. Nowadays, that's usually not a problem. We can use what's called best subsets regression. That means for any given number of variables, we ask what is the best and maybe the second best model with that number of variables, and then review those models to see which ones make sense in terms of our theory. Now, I said that we can't use R² as a useful way to choose the best model because that would simply choose the most complex one. I said that adjusted R² was a bit better, but it turns out still not perfect. So let's think a little bit more carefully about model selection. As I said, one thing we should obviously do to start with is compare the simplest and the most complex model. That's our f-test, our overall f-test. And if that's not significant, we should stop, as that suggests that everything we observe, other than the variability links the variables in the simplest model, is just random. So we should just use that simplest model, which is usually the null model with no independent variables, but it might, of course, in some cases still have our control variables that we want to remove even in the simplest model. On the other hand, if that is significant, that means that our simplest model is not good enough. So for those of you who took my course before, will remember we talked about Occam's razor or Occam's law. If you don't know about Occam's law, I encourage you to go back and read the course book, to read the section on Occam's law. Occam's law says we should choose a model, the best model, right? The best model, how do we choose the best model? We choose the simplest model where there isn't a better model. In other words, if I'm comparing two models, unless I'm sure that the more complex one is better than the simpler one, I should just prefer the simpler model. So we have a general preference for simpler models unless they're clearly not good enough. So we can use an F statistic to compare each model against the most complex model. This is called the Lattice Approach, where we can construct a tree of all the possible models. And basically we want to choose the simplest model on that tree, which is not significant when we compare it against the most complex model. So as I mentioned, this is the philosophy of Occam's razor or Occam's law. It says we should choose the simplest explanation that is adequate. So mixed stepwise regression can sometimes be a useful tool as long as we're aware of the risks, particularly of wrongly rejecting the null. So we need to be very careful about the significance level calculations if we have a large number of tests. So now I want to take a little bit of time to talk about model selection criteria. So we started out with R squared, then we went to adjusted R squared, and as we will see, we also have the F test. So let's have a look at these. So R squared out without adjustment, we've already said, is a very bad criterion because it will always choose the most complex model. Adjusted R squared is better, but it still tends to choose overly complex model. The F test is equivalent to what's called the log likelihood ratio test for linear models. So we'll see that that's the same as twice the difference in the maximum log likelihood of the two models being compared. However, this criterion has also been criticized for choosing models that are too complex. So there are two other criteria we can consider. One is called AIC and the other one is BIC. So these are more sophisticated criteria which are more trustworthy than repeated significance tests. So I'm not going to take you through a detailed statistical argument for AIC and BIC, but they're basically choosing S and P to be small together. So these criteria may need adjustment if we're considering models with different transformations. One nice thing is adjusted R squared can still be used for comparing models with different transformations. So how do AIC and BIC work? So AIC and BIC work by, we want to choose the models with lowest AIC or lowest BIC. So these are equivalent to choosing the highest log likelihood models after we have a penalty for the number of parameters. So P is our number of coefficients including the intercept, so that's the total number of parameters. AIC and BIC are based on different theoretical arguments. AIC is based on an information theory argument. BIC is based on a Bayesian analysis argument, although there is some Bayesians who don't accept BIC because they say it takes no account of any prior information. So how do these work? So AIC says we start out with minus twice the log likelihood, but we penalize it with 2p, meaning we have this penalty of 2p to take into account, so that penalizes models with large numbers of parameters. There's also a variation on AIC called AICC with an extra C. This adds in an extra term of 2p times p plus 1 over n minus p minus 1. Clearly, if n is large compared to p squared, that extra term is small. BIC penalizes minus the twice log likelihood in a different way. The penalty is p log n. So, obviously, log n is normally going to be bigger than 2. So notice this is log to the base e. So if n is bigger than 10, then log n will be bigger than 2. And so clearly BIC penalizes the number of parameters more heavily than AIC does. Now the log likelihood is a bit complicated, but for specifically our situation here with linear models, with independent errors which follow a Gaussian or normal distribution, it turns out the log likelihood, if we ignore constants, can be written as minus n over 2 log to the base e of the residual sum of squares. In other words, AIC is n times log e of the residual sum of squares plus 2p. BIC is n times log e of the residual sum of squares plus p log n. So we can see that BIC penalizes complexity more than AIC in all practical situations. And it's like starting out by saying we want to minimize the residual sum of squares, but then we need to penalize this more because the residual sum of squares always gets smaller as the number of parameters goes up. Okay, so this is how we can conceptualize this. And in most statistical packages now, most modern ones, rather than just choosing the observed significance level, you can choose AIC or BIC as your selection criteria. So these criteria are not limited to linear models, but we need to be able to calculate the log likelihood and the number of parameters. Now, one thing about AIC or BIC is that we no longer have a statistical test. So how do we decide on this comparison? Do we just choose the best AIC or BIC? Clearly, you may have multiple models which have very similar AIC or BIC. So there is an argument that differences of less than 2 in AIC or BIC are not very meaningful. It essentially means we cannot distinguish between the models. As I said, all of these criteria, except for the R squared and adjusted R squared, assume that we have the same dependent variables values. In other words, we haven't changed the y's. AIC and BIC do not require that the models are nested. So what does nested mean? Nested means all models are special cases of the most complex model. The F-test does actually require that. Okay, so in addition to this issue about which criteria, it turns out that if you use a statistical package, you also need to be careful that if you just use the default settings in that statistical package, you may not get sensible answers. So I'm going to illustrate here now the risk in accepting the default settings without careful looking at them first. Okay, so as I was saying, there can be problems if you use the default settings in statistical packages. So I'm going to illustrate here how badly things can go wrong. So we were previously looking at how to predict auction uptake in our earlier example. So using the same dependent variable as in that example, but with 30 randomly generated x's. In other words, these x's have absolutely no relationship with the dependent variable. Right, now this is an extreme example, as the number of variables is almost the same as the sample size. So p, clearly when p is large compared to n, things can go particularly badly wrong. So this is showing you what happens if you use the default settings for stepwise regression in JMP. So you'll notice it says I've managed to achieve an adjusted R-squared of over 82%. And it says that depending on where I draw the cutoff value, I've got all of these variables. You'll see many of these are highly significant, right? You'll see I've got 4 of my variables are significant at 0.01%, and I've got other ones which are significant still at 0.1%. So how did I end up with this apparently quite reasonable model in terms of the adjusted R-squared in this situation? Well, it's because the default p-value for adding and subtracting variables is set at 25% and 10%. So if you think about it, if I've got 30 variables and I set p at 25%, that means I'm going to end up with 7 or 8 variables just by chance, even if they're all noise. And given that I'm doing this repeatedly, I end up with an even more extreme problem. So in fact, if we set the default p-values down to 1%, then we would get the null model, because it turns out the most significant variable on its own only has a p-value of about 3%, which is about what we would expect, right? We have 30 variables, so the smallest of 30 values randomly between 0 and 1 we would expect to be about 1/30. So if there was no association, we would expect to have one variable significant at 3%. But once you start putting combinations of variables in, things can go very seriously wrong, particularly if you don't explain how you got to this and the fact that you have sorted through 30 variables to get to this set. As I said, this is a very extreme case because we have 31 data points and 30 variables. So this is really a very bad outcome. Okay, so now we're going to move on to the other side. When we were looking at the simple linear model, we said there was necessary to look at diagnostics. Now, diagnostics didn't seem quite so important with the simple linear model because the simple plot of y against x should normally tell us if there is some problem with our fitted model, right? So remember, we had one case where it was clear that the correct fitted model was a quadratic, and we had another one where it was clear there was one data point that didn't fit the model that fit the rest. So that's not too hard to identify if you only have one x and one y. But if we have more than one x, it turns out to be much more tricky to identify if there is some problem with our fitted model. So what are the diagnostic tools? So the two core diagnostic tools are the residuals, which we've already met before, and influence or leverage. So the residuals are telling us what the fitting error is for each point. Influence or leverage values tells us how much the model depends on each point. So it turns out they actually depend on that H hat matrix we mentioned before. If a diagonal coefficient of H is large, that means this data point has a very large influence on the fitted model. That's because the fitted value of y is H times y. So the ith fitted value is just the ith diagonal element of H times the observed yi plus some other terms. So we will see that the statistics package can show us how big the HII values are, and hence warn us whether some of the data points may be very influential in terms of our fitted model. Now, the residuals can be used in several different ways. They can be plotted in sequence to see if there's a pattern in the sequence. What we did before was to plot them against the fitted value to see if there's some nonlinearity in the overall response, or they can even be plotted against each independent variable to see if there is nonlinearity for each variable. And of course, we can also look at the distribution of the residuals to see if they follow a normal distribution, meaning a bell-shaped curve. So we're going to talk about that part later. The leverage plots, as I said, show the influence of data points on the model, either overall or in terms of each independent variable. So I'm going to show you a data set that has 3 predictors: aperture, ranging, and cadence. And the thing we're trying to predict is yield. And this data set is going to look very good because the adjusted R-squared is over 99%. However, as we will see, one of the data points is highly influential, and I have marked it with a plus symbol so that you can easily see it in the plots. And I want you to notice that the coefficient for cadence is positive, while for aperture and ranging, they are both negative. So let's have a look at our outcome. So if we first of all look at the graph on the left, this is fitting the actual y's against the predicted y's. You can see this looks very good. The adjusted R-squared is 99.6%. You can just about see the plus symbol somewhere along that line, right? So, but it doesn't look to be a big problem. Our model looks really good. And you will see that all 3 of our x variables, aperture, ranging, and cadence, are all strongly significant at 0.01%. As I said, aperture and ranging have a negative coefficient and cadence has a positive coefficient. But if we look on the right-hand side, these 3 plots are showing us the leverage in terms of each of the x variables. So you will see the plus symbol is quite extreme on all 3 of these variables. So you'll see that it has a large leverage on aperture, a large leverage on ranging, and a large leverage on cadence. So that implies, those high leverage imply that if we remove that 1 point from the fitting of our model, there may be an important change in the fitted model. Okay, so how can we illustrate that? What we can do is refit the model with that 1 data point excluded from the model fit. Okay, so remember, we already have a very high adjusted R-squared. We already have all 3 variables are strongly significant, and we have roughly -0.6, -0.6, and 2.8 as our 3 coefficients. So this is now showing you what happens if I exclude the plus data point from the fit. If we now look at this, you'll see the adjusted R-squared has now jumped up to 99.96%. And you can see that the plus point looks quite different from the fitted line through all the other data points. But look at what's happened to the coefficients. Aperture and ranging were both very strongly negative significant. They're now both very strongly positive and very strongly significant. And cadence has changed quite drastically, but is still significant. So the parameter estimates for aperture and ranging have changed sign. The size of the coefficient for cadence has changed quite drastically. How can that be? Right? How can removing a data point which didn't appear to be a big problem suddenly lead to such a major change in our fitted model? So what I'm going to try and do for you is to do something a little bit like what we did with the Longley data set, but this time we're going to be a little bit more sophisticated. With the Longley data set, I showed you the scatter plot of the x's, meaning each pair of x's. What I'm going to do here is to show you a 3D plot of the 3 covariates to try and show you that that point with the plus contains information quite separate from all the other data points, as all the other data points are in a single plane. So let's have a look. So if you look at this, you will see all of my dots, my black dots, are pretty much in a straight line here. And you can see that the green plus is quite distinct from all the other points. In other words, this is saying that that one individual data point contains very separate information from all the others. Right? Now, maybe that does or doesn't matter, but in this case, it does matter. It made a very big difference to our parameter estimates. So one of the problems is that without the plus data point, all our other data points lie in this one plane. So they don't actually tell us very much about how the yield depends on these three variables. It only tells us how it varies within that plane. It doesn't tell us how it varies within the whole 3D space. So we're very dependent on that one data point. So unlike the example with the simple linear regression, this does not mean that the model without the plus data point is the correct one and the one with it is wrong. It's telling us the problem here is that we only have one data point in that extra direction, right? So this is clearly a failure in terms of how the cadence, ranging, and aperture were chosen or selected, that you've got just this one data point that's the only one that tells us how the yield changes if you move in that dimension separately from the other dimensions. Okay, so what haven't we looked at yet? We haven't yet looked at this crucial assumption of normality tests, right? So even when we started with a simple linear regression model, we said that the core assumptions were independent errors and constant variance, but we said in order to do the statistical tests, we also needed to assume that the errors independently follow a standard normal distribution. Sorry, not a standard normal distribution, a normal distribution. Now, one thing that people often don't understand, when we're just looking at how well the sample mean predicts the population mean, one of the nice things is if we have a big enough sample, the sample mean approximately follows a normal distribution, meaning as long as the sample's big enough, we don't need to worry too much what the original distribution was. However, with linear models, a large sample doesn't make the assumption correct. So it still matters what was the distribution of the random errors. Now, there are different ways of testing the normality, formal tests, but most of them I don't find particularly helpful because they don't really tell you in what way the data might not be normal. So what I'm going to illustrate is a graphical method. What it does is it plots the residuals in increasing value order from most negative to most positive, and it plots them against what those values would be expected to be if they really did come from a normal distribution, right? So we're plotting the residuals against their expected values if they come from a normal distribution. So this is actually going back to the simple linear regression example from before, the growth one. So if you remember in the growth one, when we plotted the residuals, we could see they had a very strange distribution. So you can see here, so what we're expecting is if the distribution of the residuals is normal, we should have our data points lying along that red diagonal. Right, so the red diagonal is where we want our data points to appear if the residuals are approximately normal, and the two dotted red curves are the confidence limits on our residuals if they really do come from a normal distribution. So in this case, we can see quite clearly that the residuals go outside the confidence limits, so we would clearly formally reject a test of normality for the residuals, but we can also see in what sort of way they are non-normal. So you can see there is a very asymmetrical element, and if we look on the left-hand side, we can see the histogram for the residuals. And you can see this is not a symmetrical distribution. We've got some very large negative values, and generally this is not very nice. So clearly there is a problem in this particular case. Okay, so we've looked at the diagnostics, we've looked at the residuals themselves, we've looked at the leverage, we've looked at whether the residuals follow normal distribution. But what about other possible approaches? So the growth curve, we want to come back to that one again, because one of the other possibilities for a multiple regression model is polynomial regression. So polynomial just means powers of x. So in this case, the question would be, what order of polynomial x could we use to fit the model? So generally, we don't like high order polynomials too much because these models often give quite extreme predictions outside the data range. So this is one reason why we'd often prefer looking at transformations instead. But I want to illustrate this through the growth example. So on the left-hand side here, we again have the growth curve example we looked at under the simple linear regression. But what I'm showing you here is not the simple linear model, but the fifth order polynomial. So that means it has age in it. It has age squared, age cubed, age to the fourth, and age to the fifth. And if you look on the right-hand side, you'll see at the top we've got what the equation is. So you can see it's a very complicated model, right? We have 5 coefficients plus the intercept. And if you look at the bottom of the right-hand side, you will see that all of these coefficients are significant all the way up to the 5th order polynomial. In fact, the 6th order polynomial term is not significant. So this makes it appear that maybe if you took the approach of fitting polynomials, if you look at the adjusted R squared, you'll see the adjusted R squared is 96%. So this is slightly better in terms of adjusted R squared than the model I got with the log-log transformation before. However, the problem is I have this very complicated model. So this is slightly better than I got from the simple log-log transformation, but it's very hard to explain. How can I explain to a pediatrician, this is what's going on, this is my explanation of how the ratio changes with age? So polynomials are sometimes useful in the sense that all I want to do is to fit a smooth curve through my data points. And I'm not particularly interested in interpreting that model as something meaningful. But you can see that this model actually doesn't fit that much better than my simple log-log transformation. And as I said, this one, how can I possibly explain the 6 terms in this model as opposed to the log-log one, where I only had 2 terms to explain? So it's a much more complicated model, but it's not actually that much better. So let's look more carefully at transformations. So we're going to look at 2 types of transformation. The first type we're going to look at is what's called the power transformation. So the power transformation means we change from y to looking at y to the power of a, where a is some parameter for us to adjust. But rather than just looking at z equals y to the power of a, you'll see I've put y to the power of a minus 1 over a. So why do I do it this way round? Why not just look at y to the power of a? Well, it turns out that there's a very good reason for writing the transformation this way. That reason is because I'm interested in the situation where a is close to 0. Now, y to the power of 0 is 1. So my numerator is 1 minus 1, but a is also 0. So I have something that's close to 0 divided by something that's close to 0. Well, it turns out if we use calculus to find out the gradient of this function, the limiting case is just z equals log y when a is equal to 0. So that's very nice because it enables me to look at this whole class of possible transformations, which includes the log transformation. So it includes a equals 1, just means no transformation at all. A equals 2 is a quadratic transformation. A equals a half is a square root. A equals a third is a cube root. A is 0, as I said, is log. So this gives me a number of different possible transformations all within this same set. So log is particularly interesting because log makes special sense when we have either product or ratio variables, because it turns products or ratios into linear relationships. So log of y1 times y2 is just log of y1 plus log of y2. So we have an additive relationship. Log of y1 over y2 is just log of y1 minus log of y2. So I've just turned that into a subtractive relationship. So we've already looked at this in the growth example because that explicitly included ratios. So that log ratio then just meant the log of the numerator minus the log of the denominator. Now there are some specific situations where transformations may actually simplify the model. So for example, if we were trying to model weight and height, we would expect that weight should be proportional to some power of height. So for example, log weight would then be linear in log height. So it's important to think about models that make sense, meaning they have a sound theoretical basis. So there's another nice example I want to show you, which is about predicting the volume of trees given the diameter of the tree and the height of the tree. So I'm going to show you what happens if we do a regression model using the original raw data and if we do a log transformation. So it turns out, as we will see in a minute, the log model fits better, at least in terms of the adjusted R squared, but the log model has another big advantage. So think about the formulas for the volume of the tree. So if you think about what does a tree look like, so depending on the shape of the tree, you might imagine, if you're thinking of, say, a Christmas tree or a pine tree, that they're approximately a cone, right? Or you might have a different type of tree which is approximately a cylinder, right? Or you might even have another tree which is approximately a sphere. So in all of those situations, the volume of a cone or a cylinder is proportional to the square of the diameter times the height. So the coefficient may vary, but we still have v is proportional to d squared h. So what does that mean? So that means if we take logs, we would expect that log of volume is a constant plus twice the log of the diameter plus 1 times the log of the height. So let's have a look. Does that map well onto what we get in our data set? So on the left-hand side, we have the original model, which just has in it diameter and height as covariates. And you'll see the adjusted R squared is about 94%. In fact, if you look at the plot of the data, you'll see the plot doesn't look too good. There's a little bit of curvature in that plot. If I did the residual plot more carefully, you would see there is probably a missing quadratic term in here. But you can see that the diameter is strongly significant and the height is significant at about 1.5%. Okay, so that's one possibility. So let's compare that to the one on the right. So the one on the right has the same level of complexity. We again have two variables, two covariates. This time we're predicting log volume in terms of log diameter and log height. You see the adjusted R squared has jumped to 97.6%. In fact, if we look at the residual plot for this, the residuals look very nice. There's no pattern left at all. And again, both the covariates are significant. This time they're both very strongly significant. But interestingly, look at the coefficients for log diameter and log height. The coefficient for log diameter is 1.98 with a standard error of 0.075. So you can see that 2 is well within the confidence interval for the log of diameter coefficient. So that makes sense. Remember I said that V is proportional to D squared. And we look at the effective height, the coefficient is 1.12 with a standard error of 0.2. So the coefficient for log height is close to 1. Well, 1 is well inside the confidence interval for the coefficient of log height. So that suggests that I could even try the model that just says log of volume is equal to twice log diameter plus log height and test whether that coefficient is equal to 1. And indeed, I can tell you it fits very nicely. So that's a much simpler model. In other words, I can go back to my friend and say, yes, the volume is proportional to diameter squared height with this constant of proportionality, which explains nearly all the variability in my data set. So interestingly, the example on the left-hand side, you will find it in some statistics textbooks. And they show this as an example where after looking at the residuals, you decide that you need to also include diameter squared. So in other words, they end up with a model which is more complicated than the model on the right, but it still doesn't fit as well as the model on the right. And it's very hard to make sense because volume, the units of volume are centimeters cubed, whereas diameter and height are both centimeters. So how can I possibly interpret the model on the left-hand side? It doesn't make sense. Whereas the model on the right makes scientific sense and it fits better. Okay, so the last possibility that I want to consider is transforming using ranks. So this seems a little bit odd. How is ranking a transformation? Well, what we're going to do is to replace the data by their ranks from 1 to n. In other words, we sort our data from small to large, and we replace their values by their rank in that sorting. So this is actually usually equivalent to what we call a non-parametric procedure. So this is usually a less powerful procedure in the statistical power sense, but it's based on weaker assumptions, so it's more robust. The slightly tricky point is how do we handle ties? In other words, values with the same rank. So what we generally will do is put the average rank for any tied values. So there is one slight problem that proper non-parametric methods also account for the fact that ties reduce the variability. So we actually have less information. So again, I want to illustrate this with the growth example. So what I've done here is my y variable is now the average rank for the ratio, and my x variable is the rank average for the age. Right, so I'm plotting y against x, but now my ranks go from 1 to 72 for both the age and the ratio. Interestingly, you will see the adjusted R squared is again about 95%. And the coefficient of the rank average age is very close to 1. We're only about 1 standard error away from 1. So it's essentially saying that the rank average ratio is something like 1 plus the rank averaged age. So that's very close to what we want to consider. In fact, you will see the intercept is not significantly different from 0. So that says that we could argue that the average rank of ratio is very well predicted by the average rank of age. So what does this mean? This means that the ratio increases with age, but we don't know what the rate is. So the rate may vary, And in fact, that's what we observed on the original plot. But interestingly, you will see this very simple model fits just as well as my log-log transformation, and it fits almost as well as my complicated polynomial example. Right? So this is very easy to interpret. It's saying what I am absolutely certain is as the age goes up, the ratio increases. My log-log model says it's approximately increasing exponentially. Right? So those two things fit very nicely. This is a very nice example of how we can use the ranks, but we actually have thrown away very little information. We're still able to draw quite useful and strong conclusions. Okay, so that's where we're going to stop for today. Thank you very much.